This is our fourth video, and in this video we are going to look at the solutions for problems number 15 in our first exam. In these problems, we are given a linear transformation T, which takes elements in R2 and map it to R3, and has to satisfy the following two conditions. That is, T has to take 1, 1 and map it to 1, 0, 0, and T also have to take 1, negative 1 and map it to 0, 1, 0. We know that all linear transformations are matrix transformations. Therefore, the question asks us to find the standard matrix for these linear transformations. Now, the theory says that in order to do that, we have to look at the two vectors, which is our E1 and E2. So our standard basis, E1 and E2, which is our 1, 0 and 0, 1 in R2. And we need to look at the image of E1 and E2 under the mapping T. That is to say that we need to figure out what is this value. So this is a 3 by 1 column vectors. What are the 3 by 1 column vectors TE1 represent? And also we need to find out what is TE2, which is another 3 by 1 column vectors. And once we have that, we just need to construct a matrix A with the first column here, which is exactly TE1, and the second column here is exactly our TE2. The difficulty for our problem is that we do not have this information. So we do not have TE1 and TE2. We do not have T10 and we do not have T01. Instead, what we have is T that mapped. We have the information that T takes 1, 1 and map it to here. T takes 1 and negative 1 and map it to here. So in order to find out what TE1 and TE2 is, one thing we can do is to write E1, okay, is to write E1 as a linear combinations of the two vectors that is given. So we write E1, which is our 1, 0, equals to alpha 1 for some alpha 1s that we are going to figure out later. It's real numbers. So we're going to write 1, 0 as alpha 1, 1, 1 plus alpha 2, 1 and negative 1. So alpha 2 is also another real number, which we have to figure out what's the value of. So once you have this, suppose you be able to figure out what alpha 1 and alpha 2 is, then because of the linear property of the transformation T, so T10 will be alpha 1 T of these vectors and alpha 2 of these vectors. So we know these values. T11 is 1, 0, 0, T1 negative 1 is 0, 1, 0. So if you can find out what's alpha 1 and alpha 2, then TE1 is nothing but alpha 1, alpha 2, 0. Insert these columns here, then you have the first column of the matrix A. So we have seen this idea before in our homework and also in our practice exam. So this is not something that is new. And the other things is that once we have the first column of matrix A, we need to figure out what's the second columns of matrix A. So we do the same computations. We look at E2, which is 0, 1, and then we write as a linear combination of these two vectors 1, 1 and 1, negative 1. So beta 1 and beta 2 here are two real numbers, which we need to determine. Again, if we have determined beta 1 and beta 2, then T01 is going to be this by the linear properties of that transformations. We can write it like this. And again, we know the image of 1, 1 under the mapping T and also the image of 1 and negative 1 under the mapping T. So we have this. And this is going to be nothing but the column vectors beta 1, beta 2, 0. Insert this column vectors right here in your matrix A, then you will have the standard matrix for that linear transformations. So if you do that computation this way, you will find out that the A is going to be of this form. So these are the computations, and you will figure out that matrix A, the standard matrix, is going to be of this form. Now, this is utilizing all the theory that we know for linear transformations and how we use TE1 and TE2 to construct the columns of matrix A, the first column and the second column of matrix A. Another computations, which is another method, which basically just involve computation like this, will completely bypass all this theory. Instead, we look at this in a very simplistic manner. That is, we are looking for a matrix that takes 1, 1 and map it to 1, 0, 0. And because of the size of all the matrices involved here, matrix A has to be of size 3 by 2. This is 2 by 1 and this is 3 by 1. Same thing here, we need to find a matrix A that map 1 and negative 1 to 0, 1, 0. So as I said, because of the constraint of the size of the matrix, we know that the matrix A has to be 3 by 2. So we have to figure out what are the elements A, B, C, D, and E, F. So suppose we let A to be the matrix A, B, C, D, and E, F, then A takes 1, 1 and map it to 1, 0, 0 will give us this particular system of equations, which says that A plus B has to be 1, C plus D has to be 0, E plus F has to be 0. Similarly, if you look at the matrix A, which takes 1 and negative 1 to 0, 1, 0, then this multiplications will give us the system of equation, which is how A plus B has to be equal to 0, C minus D has to be equal to 1, and E minus F has to be equal to 0. Solving this system of equations will give us A equals to 1/2, 1 over 2, B equals to 1 over 2, C is 1 over 2, D is negative 1 over 2, and E and F both has to be 0. Therefore, you have a matrix A, which is exactly the same matrix A coming from that computations that we have earlier. And this is how you solve problem number 15.